Okay, we're testing the audio. We're trying to make sure the autofocus works. Will you focus on my face? That would be fantastic. We've got the Fredster. What do you have to say? The void has spoken. So that's Freddy. That's Freddy. That's the cat. That's the boy. The menace. The legend. He is the duality of man. He is violence and he is eepy. So we're testing things now because we're professional here. We're doing professional things. Well, looks like everything's working fine. I am Torin. I use he, they pronouns. And today we're going to be talking about science because I'm autistic and a nerd. Now, you may be wondering, Torin, what are your qualifications to be discussing science? And that's a great question. I will defer you back to what I just said. I'm autistic and a nerd. Those are my qualifications, no more and no less. So I will be saying things that I know and things that I have researched for the makings of this video. I might get things wrong because I don't have a degree. I'm just a white guy on the internet with a microphone. So take it or leave it. If you think I got something wrong, please research it yourself and tell me in the comments. Here we go. We're on Reddit. Surprise, surprise. White guy with a microphone on the internet and Reddit. I'm sure you're very shocked. We're going to be discussing things that I'm getting from the r/askscience subreddit that are just general questions people have about science, and we're going to be discussing them. First question. What's with the apocalyptic floods we're seeing more and more? Europe, India, Pakistan, China, Brazil, Kenya, Russia, Australia, and others. It feels like everywhere now there are massive, never-seen-before floods happening. Or maybe I'm just focusing too much on negative headlines, and floods aren't getting that much worse or more frequent. I don't know. I assume climate change is to blame somehow, but how exactly does it tie to this insane prevalence of heavy floods on a global scale? That's a great question. Big floods, climate change, weather patterns. All buzzwords that you're hearing. What do they mean? Maybe I'll know. Freddy is back. With climate change, we have more greenhouse gases in the air. Those greenhouse gases are causing higher levels of energy from the sun being trapped in the Earth's atmosphere. When air is warmer, it has a higher capacity to hold water. So when we have these extreme weather patterns, we have air that has much more moisture in it than it did before or than it should. And suddenly, all of that water can come out of the air in what we call rain. In all of this rain, we get flooding. And flooding happens naturally. That's a natural weather phenomena. Flooding happens. Climate change makes this problem worse because there is more energy and more water within the air. And also, when a gas is heated up, it expands. That creates more pressure, which pushes out into other areas. So you get areas of high pressure, areas of low pressure. Welcome to weather. Welcome to wind. So that plays a role in some things. It causes extreme weather patterns when it comes to hurricanes, tornadoes, high winds, clouds moving all over the place where they might not normally. And then we get flooding in places sometimes where there wouldn't normally be flooding because there is expanded air pockets in certain parts of the world, and that causes cold pockets in other places and hot pockets in some spots, and it's complicated is what I'm saying. But hopefully that answered that question, and I'm not just rambling. I think I am rambling, but maybe you learned something. We'll see. Next question. How come if we jump inside a train, we land on the same spot, but if jumped on top of it, we land on a different one? So that's a thing we like to call inertia. When something is already moving, it's going to keep moving unless something stops it from moving. That's Newton's something law of physics. So if you're in a train and you jump, you are already moving. So you're going to keep moving at the speed the train is moving unless something stops you. For example, air resistance. If you are on top of a train, there's a bunch of wind coming at you because you're moving into the air. That causes air resistance. You jump up, there's air there. That air will stop you from moving forward as fast as you would have otherwise. That is the thing stopping you from moving, just like a wall would be if you're driving a car into a wall, which we'll see if I'll do later. So, the answer, inertia, keeps you going, and if you were on top of a train, wind resistance would stop you from going. If birds evolved from dinosaurs, what natural selection feature of the birds made them evolve to a much smaller size compared to dinos? So, generally, it is easier for organisms to exist if they are smaller because they do not need to get as much food, right? You're bigger, you have more body to move around, that requires more energy. So, a lot of times, species will become smaller because you don't require as much food that way. One factor that may have played a role in dinosaurs becoming smaller, aka birds, is that there is less oxygen in the air now. That's probably not a huge aspect of it. That more plays a role in insects, invertebrates being large, but probably had some effect on vertebrate size, I would imagine. Also, though, when we make generalizations like birds are smaller than dinosaurs, it's important to remember that there were very small dinosaurs, and there are relatively large birds. Right? Ostriches, the world's largest bird, are pretty fucking big. Much bigger than a lot of dinosaurs that existed. And we're talking ancient dinosaurs, not modern dinosaurs, which are birds. And there were dinosaurs that were the size of a chicken, right? Velociraptors were about the size of a turkey. They were pretty small. So we generally think of dinosaurs as being huge, right? But dinosaurs varied a lot in size. So part of this may just be that birds are just the small dinosaurs that survived. A lot of it is just that it is more efficient and easier to live on Earth when you are smaller because you don't need as much food, you don't use up as much energy. Moving on. If birds are descendants of reptiles, how and when did they become warm-blooded? So, the premise of this question isn't entirely accurate. So, if birds are descendants of reptiles, birds are descendants of dinosaurs, which were a type of reptile, but somewhat different than modern reptiles, is my understanding. For birds, the specific ancestor is theropods. Birds are theropods. We will go to Wikipedia. Don't come at me. Wikipedia is fine to use for things. I'm not writing a fucking article. We have Dinosauria right here. Dinosaurs. Under that, Theropoda. Those are theropods. They're a type of dinosaur that includes T-Rex, velociraptors, other bipedal dinosaurs that have hollow bones, generally have 3 forward-facing toes. That's a theropod. You can read what's there. And then there's a couple other categories, and then we get down to birds. Birds are a subcategory of dinosaur. Birds are avian dinosaurs. What we typically think of dinosaurs from way back when, millions of years ago, those are non-avian dinosaurs. There are 2 groups of dinosaurs, but birds are dinosaurs as far as the taxonomy goes. Dinosaurs, in general, are thought to be warm-blooded. Editing Torrent here because I forgot some important information. So while birds are theropods, reptiles are... So, the car has hit the metaphorical wall, and the wall's name is Dunning-Kruger. I've spent at least an hour trying to figure out how reptiles evolved. Modern reptiles, that is. And I thought I knew. I assumed that modern reptiles and birds both evolved from different dinosaurs. But I was mistaken. So that is why you are now getting this meta editor torrent on top of editor torrent. Because I think, after vigorous Googling, I have figured out where the fuck modern reptiles came from. Because it wasn't dinosaurs. So, here's what I have. If I'm wrong, feel free to correct me. Back during the Carboniferous, which was a period of time, it is back when they had those giant dragonflies, the big centipedes, all that shit. It's back when coal was created. That's the era all that comes from. Back during the Carboniferous, there was an ancient amphibian, okay? That ancient amphibian evolved into a bunch of different shit. It evolved into a lineage that goes down to modern reptiles. It evolved into a lineage that went to dinosaurs and then birds. It evolved into a lineage that went to modern amphibians, and it evolved into a lineage that went to mammals. Yeah. So this one thing is the ancestor of all those groups. And it's complicated. I'll put a couple of phylogenetic trees in here so you can kind of visually see how all that links to each other. But what I'm trying to say is that modern reptiles did not come from dinosaurs. Modern reptiles evolved completely independently of dinosaurs and birds. So now I know. And now you know. We've learned together. Anyways, back to whatever the fuck I was saying before. There's a lot of debate in scientific communities and paleontology communities about if dinosaurs were warm or cold-blooded, and it's thought by many that it may have been some dinosaurs were cold-blooded, some were warm-blooded. So really, birds never became warm-blooded, they always have been, because they evolved from dinosaurs that were warm-blooded in the first place. Think of where reptiles generally live. Generally, they live in warm places, right? You're not going to find reptiles in Antarctica. They don't like it there. It's cold. They don't produce their own body heat. They cannot regulate their internal temperature. They live in warm places. So the closer to the equator you go, the more you're going to find reptiles. And so why, then, did they become cold-blooded? Because they didn't need to produce their own body heat because they already live in warm places. So it is advantageous for them to not waste their energy on producing body heat because they can just get that from laying in the sun. So now, since they're not producing body heat, they can use all that energy they were using for body heat for reproduction, for movement, right? And so that's the advantage there. If it's more advantageous, a lot of times species will evolve to do that. Not every time. Science is inconsistent, evolution is inconsistent. This is all based on chance, right? But that's what will often happen. A little bit deeper, this is a good little thing about reptiles and about body heat, all that shit. There's a bunch of different words. There's homeothermic, poikilothermic, endothermic, and exothermic. You can read these to see what all of those mean, but basically body heat, or the amount of body heat a species produces, is on a scale. Every species, if they do produce body heat, produces a different amount, right? Humans are 98.7, or I think that's right. Dogs have a slightly higher body temperature, like 101 or something. And then some animals have little to no body temperature that they produce themselves. And so these words help define if an organism can produce their own body heat or not, and whether or not they can regulate their own internal body temperature, which is a slightly different thing. Again, you can read it on this thing on the screen. What was in our area of space before our sun existed? Okay, so this one's kind of tricky because how do you define what our area of space is? Outer space, the universe, is in general a vacuum. There's not much there. The universe is mostly empty space. So talking about a specific spot in space is kind of tricky because it's all relative to other objects. And so within our solar system, our whole solar system is moving together through space, through our galaxy, and the galaxy is moving relative to other galaxies. So in our area of space doesn't really mean much when we're talking about outer space. But if we're just talking generally, what existed in space before our solar system? Dust, gases that eventually came together due to gravity, pressure from the gravity holding all of that in, created nuclear fusion, boom, a star, other shit orbited around the star, created planets, blah, 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 you get the rest. So what was in our area of space before the sun existed? I guess you could say dust and gases. Voyager spacecraft just lucky? If the JWST, or James Webb Space Telescope, has already experienced small injuries or damage from micrometeors or other fast-moving dust and debris, how is it that the two Voyager crafts seem to have escaped such damage? So there's a few factors that come into play there. They're talking about the James Webb Space Telescope taking damage from small meteors or just, space debris. I think a large part of that is where the James Webb Space Telescope is. The James Webb Space Telescope is in one of the Lagrange points, which is an area of gravitational equilibrium between Earth and the Sun. I'm back. So, correction, the James Webb Space Telescope is at Lagrange point 2, which is on the other side of Earth relative to the Sun. It is not between Earth and the Sun, but it is at a point of gravitational equilibrium. It's complicated. I don't know all the math behind it. But anyways, it goes Sun, Earth, Lagrange point 2. Lagrange point 2 is about 4 times farther away from the Earth than the Moon is. So, there you go. So basically it's just at the sweet spot that it stays there. So because it is within that kind of orbit, there's a lot of stuff in there. And that specific spot where it's at is an area of equilibrium where a lot of stuff might end up. So I would imagine becomes kind of a target for a lot of space debris just based off of where it is. Now, the Voyager spacecrafts traveled very quickly away from Earth towards the outer solar system. And now both Voyager 1 and 2 are outside of our solar system. They're in interstellar space. So there's barely anything where the Voyager spacecrafts are at now. So it is very, very, very unlikely that anything would ever physically hit the Voyager spacecrafts because of where they're at. You know, they left the solar system relatively quickly, so there wasn't much likelihood of stuff hitting them. Also, I don't know how much this would play into this because the James Webb Space Telescope isn't that close to Earth, but there is a lot more space debris caused by humans that is orbiting Earth now that causes problems when launching things into space. So it would make sense that now the James Webb Space Telescope gets hit by more things than the Voyager spacecrafts did being launched, in the 70s, I want to say? I don't know how much that would play into it, but probably some. So, long story short, Voyager spacecrafts wouldn't have been hit by things because they were moving very fast out of the solar system, not much stuff for them to hit. James Webb Space Telescope is in a spot where it's more likely to get hit by things. How does the anatomy of the eyes prevent water from entering the ocular cavity? Is there some biological watertight seal? Why doesn't water get in when, say, diving or when rinsing one's eyes in the faucet? So a lot of people kind of visualize eyes as just being this standalone ball that's in the eye socket, but there's a lot of other stuff in there too. There's muscles and all sorts of tissues surrounding the eye that attach the eye to the eye socket or to the tissues that line the eye socket. So it's not like there's just an opening that goes all the way from the front of your eye all the way back into where your optic nerve is. There's not an opening there. Things can't go through there unless there's damage, of course. But there are muscles on the top, bottom, and sides of the eyes that allow them to move up, down, left, and right. And so those muscles are physically attached to the eye. So there's not room for stuff to do that. And also the comments below go into much more detail about that. The white of your eye, the conjunctiva, is the skin that acts as a barrier between the orbit and the outside world. So yeah, there's skin there, tissue, muscles around your eye that would prevent anything from getting behind your eye, typically. Assuming you don't have ripped muscles and skin around your eye, which I hope not, because that sounds painful. Why are cats' fur just a mix of 3 colors? Orange, white, and black. So generally when we're talking about pigments and hair, skin, and even in plants, right? When plants' leaves and fruit change color, it's generally because 1 or 2 pigments is responsible. So with humans, right, we have melanin that's in our skin, in our hair, and the amount of melanin we have determines the color. And it's mostly on a scale. There's a couple different types of melanin, uromelanin and pheomelanin. I don't know how to pronounce that. Anyways, there's a couple different types of melanin, but basically the more melanin you have, the darker your hair is going to be. Same with cats. And so it goes from on one end having no melanin, or albino in some cases, where when there's no melanin, it is white, right? The hair will be white if there's no melanin. So a white cat has no melanin in their hair. Or if there's a lot of melanin on the other side, the hair will be black. And then in between is the whole spectrum of hair colors. So we have white, orange, red, and then we get browns, and then darker brown and black. And that's kind of the spectrum of hair colors in mammals. And that's just caused by the amount of melanin. So why do cats have a mix of just 3 colors? I mean, there is more of a spectrum in cat hair or hair in general than just 3 colors, but we generally identify about 3 colors. A good example in plants is tree leaves in the fall. It goes from green to red. Green, yellow, orange, red. green, yellow, orange, red is generally how we categorize those colors. So yeah, there's your little fun facts of the day about pigments in organisms that make things different colors. When experts study volcanic eruptions that happened thousands of years ago, how do they know how tall was the eruption column? And in the comment right below here reads it pretty thoroughly, but I'll give a little TLDR. Basically, scientists can see how far debris from a volcano ended up from the actual eruption, and using math determine how high that column of debris, of smoke, ash, whatever, from the volcano was in order to be able to spread debris that far. The answer is scientists know math. Do I know what math they use? No, I do not, but I know they use it. Why mountain peaks are made of rocks while others are made of soil. So what is soil? Soil is generally decomposed plants. Plants that have grown and died and grown and died and grown and died over and over again. That creates soil over time. So if a mountain has soil on top, it has plant growth and probably not a lot of erosion because soil has been able to stay there. So if we're seeing at really high elevations that a mountain peak doesn't have soil on it, that's probably because it doesn't have suitable conditions for many plants to grow. Therefore, it's just bare rock. But a lot of times mountain peaks at lower elevations will have more soil because there's plants growing there. Is climate change reversible, or is our goal simply to stop its progression before it gets any worse? I was listening to a podcast, which admittedly isn't the most informative or correct, when the host started talking about climate change and potential solutions. They joked they could take the heat and move it somewhere else, when one of them realized that with the carbon better capturing the heat, we really can't get rid of it. The problem of climate change, from what I understand, is that the atmosphere is trapping CO2 at a higher rate. There's excess energy. Hello, Fred. There's excess energy in an enclosed environment. If it was localized weather, I guess we could just move it away. However, this energy is everywhere, which kind of screws us, I assume. Clearly, my understanding of climate change is lacking. Okay, so is climate change reversible? It was. Now we're a little bit too late to completely reverse it. We are definitely already experiencing the effects of climate change, so it's kind of too late to reverse it. But yeah, the main goal now is to stop it getting worse, which includes not emitting as many greenhouse gases, or any, ideally, and taking other actions that stop runaway greenhouse gas effects. What does that mean? So that includes things like ensuring that permafrost in the Arctic stays frozen so it doesn't let out more greenhouse gases that create these just runaway effects where the warming lets out more greenhouse gases, which makes it warmer, which lets out more greenhouse gases. You can see the issue. So yeah, it's really making sure it doesn't get worse at this point. Also, in this, they say the problem of climate change, from what I understand, is that the atmosphere is trapping CO2 at a higher rate. That's not really what's happening. The atmosphere is trapping energy, heat, at a higher rate, and that is because there is more CO2 in the atmosphere. The CO2 itself isn't being trapped at a higher rate, it's just being emitted at a higher rate. It's kind of a small detail, but technical correction.
Technically correct. The best kind of correct.
So, thank you for watching. I'll get the cat. Oh, the boy. The void. He's here. What do you have to say, Freddy? Well said. Thanks for watching. Subscribe if you feel like it. Don't if you don't. Bye.